paper is a contribution from Shell Development Company in Houston, Texas. The title of the paper is Investigation into the Stacking of Molybdenum Disulfide Layers in Hydrotreated Catalyst. The author of the papers are Robert C. Ryan, Richard A. Kemp, John M. Smagel, David R. Denley, and Dr. Ryan will be presenting the paper.
Thank you. First of all, I'd like to thank the organizers, particularly Dr. Otelli, for letting me present this material. If I could have the first slide. What I've decided to do is change a little bit and to expand a bit on our stacking molybdenum disulfide layers by giving a little background information in terms of the process we went through to get to our final conclusions. This, like Russ's paper, is a joint effort from a number of different disciplines: the catalysis department, myself, Rick Kemp, John Schnagel, and the analytical department, Dave Danley, who was responsible for the XPS work, and Gerard Spindler, who did the high-resolution transmission electron microscopy, whose work done at the West Hall Research Labs in Houston, Texas. Our rather ambitious research goal was to develop an understanding of the active site or sites in aluminum-based nickel moly and cobalt moly hydroprocessing catalysts. To give you some feeling about why we think this is important, although Russ gave a very good introduction to what I'm going to be talking about, we take a look at the background work. There is a tremendous amount of excellent literature on the active sites, primarily concerned with hydrodesulfurization, usually on cobalt-promoted catalysts on a wide variety of supports. Being from an industrial lab, however, the commercial use of nickel moly catalysts is by far the most important. To give you some feeling for this, approximately 55 million pounds of catalysts, hydrotreating catalysts, sold to North America. This is the non-residue market. Over 70% is the nickel moly, while only 30% is cobalt moly. Might also point out that a large majority of it is nickel moly with phosphorus promoter, and the majority of the cobalt promoted systems are just cobalt moly with no phosphorus. This will become important later. Industrially, what the marketplace tells us is that nickel-promoted catalysts are primarily used for hydrogenatification, and cobalt-promoted catalysts primarily used for hydrodesulfurization. When we started this work a number of years ago, we felt that the current theories of active sites did not adequately address these very real differences between cobalt and nickel catalysts, and ignored, for the most part, what we feel is the important role of phosphorus promoter in alumina-based systems. How do we approach this problem? We prepared a series of catalysts that we'll see in a few slides by using a single-step dry pore volume impregnation on a gamma alumina extrudate. We studied it by a number of different techniques. Two of them I'll emphasize today: X-ray photoelectron spectroscopy and high-resolution transmission electron microscopy. We want to first examine the effects of nickel moly and cobalt moly ratios over limited range, and the role of phosphorus promoter also on catalyst activities. To combine the analytical work and the catalytic testing results to observe any differences between the nickel and cobalt catalysts, and finally to postulate a role of these promoter atoms on catalytic activity. Now, as Russ pointed out, there are a number of theories in the literature. Three that have received the most work, although we'll hear more about other theories later in the week. First is what is called the pseudo-intercalation model, work done at Shell in the early 70s, which suggested that if you had a tungsten disulfide, multiple layers, what you would have is, from ESR evidence, nickel +2 residing at the edges between the van der Waals gap in the tungsten disulfide layers. Another theory in 1973, Russ alluded to, is the work by Delmon talking about the contact synergy model. There, we've simplistically used cobalt 9S8 as a cube, and where this cube would interact with the molybdenum disulfide, that close interaction would cause electron transfer, hydrogen atom spillover, and that would be the active site. Most recently, a large amount of excellent series of paper by Topstone co-workers on a COMOS model suggests that on a wide variety of supports, alumina in this case, you have cobalt, again, sitting at the important edge of a MOS2 crystallite, but in this case, it's a single layer. So with those hypotheses, what we decided to do was look at a series of 8 catalysts. 2 of them cobalt moly, 2 of them moly only, and 4 of them are nickel moly phosphorus. As I said before, all of them were single-step impregnation on 16th-inch cylinders. The properties of the alumina carrier are here. And the weight loadings range from about 16 to 18%. What we did is kept, for this series, the total moles of metal, nickel or cobalt and moly, constant for all the catalysts at 1.87 millimoles per grain of catalyst. The metal loadings were chosen because those were metal loadings of commercially interesting catalysts. Each of the catalysts is identified by its metals and its molar ratios. There's a mistake on this slide. This should be 0.5. As you can see, the interaction of these metals, particularly those that were acidic, there's large loss of surface area upon impregnation. All catalysts were sulfided with 5% H2S in hydrogen at 350 degrees centigrade before either the catalytic testing or the analytical techniques that were used. One of the first techniques we wanted to look at is XPS, again to look at trends, mainly because XPS can probe the catalyst surface that we're obviously interested in, is sensitive to the nickel, molybdenum, and cobalt of interest, and can discriminate against the alumina substrate. What we hope to do is to compare the different metal dispersion of the catalysts, although the XPS intensities will also have contributions from bulk loading and also surface areas that we have in a very simplistic model try to take into account. So we've defined a dispersion number with the first term that would normalize it for bulk loading. We would take the surface atomic ratio from the XPS, for example, molybdenum to aluminum, divide that by the bulk atomic ratio, again, molybdenum to aluminum, that we would know from the metal loading, take into account the bulk loading differences. Surface area differences are taken into account by the second term, which also takes into account, again, in a simplistic manner, that the electrons have a mean free path of about 14 angstroms. So if you have perfect model systems, and the model systems are in our paper, for example, cobalt 9S8, molybdenum disulfide, and a perfectly dispersed system, you should have a dispersion value of 1. Obviously, for real-type catalysts, we do not have perfect dispersion, although for the molybdenum-only system, the system is fairly well dispersed. However, upon sulfiding the catalyst, there is a loss of dispersion, and this holds for both molybdenum phosphorus and the 2 cobalt moly catalysts. Might also point out that from the XPS data, we also have a significant amount of molybdenum oxide. I'll talk a little bit more about that later. I'd also point out that cobalt increases the molybdenum dispersion, while the addition of phosphorus decreases the cobalt dispersion. Now, to contrast that to the nickel-promoting catalysts, we again see some similarities, but also some differences. Again, fairly well-dispersed systems. Molybdenum decreases in dispersion upon sulfiding. The nickel results are not that clear-cut. As was found in the cobalt case, nickel increases the molybdenum dispersion, while phosphorus in this case, in distinction to the cobalt case, does not appear to affect dispersion nearly as much. Since nickel moly phosphorus catalysts are of prime importance, what we did is a small series of catalysts varying the nickel from 1% nickel to 3% nickel to 4.5% nickel. For that small series, we see that the molybdenum dispersion for the sulfide case peaks at the 0.37 case, and for the nickel dispersion also appears to be at a maximum for this particular catalyst. I'll come back to that a little bit later. Next, what we turned our attention to is high-resolution transmission electron microscopy. This again is just molybdenum, heptamolybdate water impregnated on alumina substrate. You can see the alumina substrate, and if you're in the first row, you might be able to see long curving lines of molybdenum disulfide layers identified by a basal spacing of about 6.22 angstroms. These are very long MOS2 crystallites found in the molybdenum only case. Now we've seen that cobalt has a large effect on molybdenum dispersion. How about the effect on the high resolution transmission electron microscopy? We see a tremendous difference from the molybdenum only case. Here for the cobalt promoted system, we no longer see long multiple curving layers. If you have very good eyesight, you can see where the arrows are. There are actually single layers of molybdenum disulfide throughout the entire system. So we see XPS and high-resolution TEM are showing that the effect of cobalt has a significant effect on the analytical techniques that we have used to identify these systems. Now to summarize where we are for the molybdenum only and the cobalt promoted systems, for what I've done is summarize it on this slide. Molybdenum only, as we have seen, shows multiple curving layers of MOS2 up to 800 angstroms in length. Typical basal spacing for molybdenum disulfide. Molybdenum oxide that we have seen in the XPS work, we have also seen in the high-resolution TEM. I didn't point it out in the picture, but it's a blocky molybdenum oxide. It's not molybdenum trioxide. They are covered by molybdenum disulfide. Whether it's some molybdenum dioxide or some molybdenum-aluminum interaction, we have not identified using two of these EDX and EELS technique. As we saw for the cobalt moly case, there are no multiple stacks for the cobalt moly 0.37 case. I did not show the pictures for time, but for the cobalt moly phosphorus promoted cases, we do start seeing multiple layers of molybdenum disulfide. A similar picture is seen for the molybdenum with promotion of phosphorus, showing an order of magnitude reduction in the length of the basal plane. Now, how does this compare to the nickel moly phosphorus case? Again, we see a tremendous difference between molybdenum only, cobalt promoted case, and now you see multiple layers of molybdenum disulfide throughout the entire picture. So we have seen that cobalt and nickel affect the XPS dispersion, and also that there are differences seen in the high-resolution transmission electron microscopy. Again, for time, I'll just summarize the rest of the high-resolution transmission electron microscopy results. The nickel-promoted case, as was found for the phosphorus promotion, addition of nickel causes a reduction in the length of the basal plane, no longer multiple curving layers of molybdenum disulfide. The incorporation of phosphorus increases the stacking, meaning that nickel molybdenum just by itself will have multiple layers. Phosphorus appears to increase the number of stacks. Also, I have not shown, but as the nickel-moly ratio increases for the nickel-moly phosphorus series, there appears to be an increase in the number of molybdenum disulfide stacks in these catalysts. Next, we wanted to see how our catalytic testing would look for these catalysts. This is a test using a, quote, real feed. It's a standard 3-day test that we have in the lab using whole pellets. The pressure is 60 bar. This is an engineering meeting. That's 850 pounds. Liquid hourly space velocity of 2, temperature of 343 degrees C or 650 degrees Fahrenheit. The hydrogen to oil molar ratio of about 4 to 1. After 3 days of testing, what we look at is the relative denitrification and the relative desulfurization activities based on first-order rate constants for denitrification and relative second-order rate constants for desulfurization. These are relative rate constants. What we've arbitrarily done is taken our most active catalyst, nickel moly phosphorus 0.37, that's the one with 3% nickel, and set that equal to an HDN activity of 1 for HDN and HDS, and looked at everything else in relationship to that. As you would expect, the molybdenum-only system has a very low activity for both HDN and HDS. Addition of phosphorus might slightly increase the HDN activity, while essentially does very little with the HDS activity. Not surprisingly, the addition of cobalt promotion to the molybdenum-only system more than doubles the HDN activity and increases the HDS activity by about an order of magnitude. What we are looking at is volumetric activity. This is not activity per site. This is volumetric activity for these various catalysts. Now, contrast the cobalt moly to the nickel moly case. Again, we see a large increase in denitrification compared to the moly only, but a significant improvement in HDN compared to the moly only case, while for hydrodesulfurization, we see a decrease in HDS activity compared to the cobalt moly. These numbers we feel are good to about plus or minus 10%. Next, what we did is looked at a series of nickel moly phosphorus systems. The phosphorus content of all these catalysts was 3.2% phosphorus. We did not try to optimize the phosphorus for this different series, just kept that constant and varied the nickel to moly ratio. As you can see, at the low nickel incorporation of 1%, we have a rather low activity of HDN and HDS. Increasing the nickel content from 1 to 3% significantly increases the HDN and HDS activity. Further increasing the nickel content to 4.5%, at least for this particular system on this carrier, there was a decrease in the HDN and HDS activity. So if you remember back to the XPS dispersion data, it appeared that the most dispersed system was the nickel moly phosphorus 0.37 in this series, and our activity testing results would support that. Remembering back to our background slide, where we said that industrially the most important catalysts are cobalt moly, no phosphorus, primarily used for HDS. We see that that is indeed the most active hydrodesulfurization activity, and that for HDN activity, the nickel moly with phosphorus promoter is again the most active system. Those two systems, cobalt moly and nickel moly phosphorus, accounted for 90% of the commercial catalyst market. So we feel our testing is valid for distinguishing different relative orders of catalytic testing for these systems. Now what we want to do is to make some preliminary conclusions on first the cobalt promoted case. So seen for the XPS, no stacks were found in the cobalt moly system. Addition of phosphorus caused some increase in stacking for the cobalt moly phosphorus 0.37. Higher surface coverage I won't touch on. It's part of a different model that we're currently working on. But this cobalt system first gave us some indication that the cobalt with the phosphorus promotion appeared to have a higher HDN activity, if you remember back to the previous slide, than the cobalt moly with the no phosphorus. So this first got us to thinking of a relationship between the stacking of molybdenum disulfide that we would see here and the HDN activity. First, the overwhelming evidence would indicate that the top cell monolayer model was probably correct, and that the shell model of multiple layers, at least for the cobalt moly with no phosphorus, appears to be correct. Now, to just briefly look at what a very idealized picture would be, you take a gamma alumina substrate, the oxygens are in red, the aluminum is in black, and place a molybdenum disulfide single layer on it. Molybdenums are in blue, sulfur is obviously in yellow. And if you look at a cobalt-promoted case, what you might think of is that cobalts would reside on the edges, and this would be one picture of what a cobalt-promoted system would be, and presumably what Topso is seeing in some of his work. Now that is not what is seen for the nickel-promoted catalyst. Remember, the high-resolution transmission and microscopy have shown stacks of molybdenum disulfide. Fortunately, with the techniques we've used so far, the nickel atoms cannot be located. The addition of phosphorus and nickel has a tremendous effect on the structure of the molybdenum disulfide, both of them causing a large decrease in the basal plane direction. And as shown before, as the nickel-moly ratio increases, stacks appear to increase. So in the nickel case, now we have more evidence that might suggest that the Voorhees model is correct and that the Topso model might be incorrect. Again, looking at a very idealized picture. Take a gamma-luminous substrate. The phosphorus-promoted catalysts were prepared with phosphoric acid. What we believe happens is loss of water, and you get HPO3. Phosphoruses are indicated in the light purple. Hydrogens on both the alumina and the HPO3 are not shown. And so, as with the Voorhees model, what he and coworkers said is that the nickel, again, pseudo-intercalated because it would only be on the edges, resides between the molybdenum disulfide layers, causing multiple stacks of molybdenum disulfide in the nickel-promoted systems. So what are the empirical observations that we've made so far? Addition of nickel or cobalt increases the molybdenum dispersion. That's not surprising. Addition of phosphorus. Again, remember that this is an alumina-based system. We're not talking about carbon or silica. Decreases the molybdenum dispersion. We've seen transmission electron microscopy showing multiple layers in the nickel-promoted cases, while only monolayers were seen for the cobalt-promoted cases. Addition of phosphorus and or nickel causes the stacks to increase in height. And from our testing results, cobalt-moly catalyst of choice for HDS, and for HDN, catalyst of choice is nickel-moly and phosphorus. Now, how can we put all this together? What we've come up with is a hypothesis to add to the number in the literature already, and that is that nickel and cobalt appear to do different things catalytically, and so what we propose is that they occupy different sites. One of them is that the nickel, as in the Voorhees model, is in the van der Waals gaps in a multi-layered system. Cobalt is in the molybdenum disulfide plane in a monolayer configuration. Role of the promoters, both nickel, cobalt, and phosphorus, play an important role in both HDN and HDS, and that phosphorus also plays a primary role in HDN. The question is, why is this the case? First, turning our attention to phosphorus, we know from the surface area measurements and a lot of other work, phosphorus has a very strong interaction with the alumina support and causes the catalyst to have a significantly lower surface area than those without phosphorus. What phosphorus also does is increase the density of the catalyst, which helps when you're looking at volumetric activity, though. For the molybdenum oxide impregnation, we saw that upon sulfiding, we found 800 angstrom multiple curving layers of molybdenum dioxide. What we feel happens when the phosphorus interacts with the alumina support, that this is disrupted to some extent, and that the phosphorus essentially stops the molybdenum oxide from growing in the lateral direction and promotes it growing in the vertical direction, as compared the molybdenum-moly to the molybdenum-phosphorus case. So for the phosphorus-containing catalysts, we feel that they create smaller yet taller MOS2 crystallites, and therefore the number of egg sites is increased. Now, how about the nickel and the cobalt catalysts? Well, for the nickel catalyst, which we've labeled green here, we feel that location is at the edges, molybdenum disulfide, multi-layers, and that the sites between the layers would probably require, again, an idealized situation, which probably is not strictly true, would appear to require an octahedral geometry. For the single MOS2 layer, we feel that the cobalt would reside there because the cobalt could adapt more readily to tetrahedral geometry. What is the evidence for this? Well, first we know that nickel sulfide heightened